Hello, and welcome to Reality Modeling with ContextCapture. Today we'll be looking at what is reality modeling. We'll also touch on how to capture imagery, some uses for the reality model, and finally using our program ContextCapture. Reality modeling refers to the modeling of what we can see or observe. By doing this, we give ourselves a starting point for design, building, or operations. No longer do we have to start from a blank canvas, but we can use reality as the context for these designs. In this example, a roadway has been modeled. All aspects of the roadway can now be analyzed or inspected at any stage of a project. This readily available model provides invaluable information critical to making responsible decisions. Additionally, reality models can also be used to verify design elements to monitor a site throughout its life cycle. Let's look at some other places that a reality model may be used. Here we have a model of a petrochemical plant. The reality model can be used in operation, maintenance, and design for this plant. This model can give the designer detailed information, including a scaled model, visual data such as tagged information, serial numbers, part numbers, etc., and more. On a larger scale, a reality model can be used for planning, where designers and city officials alike can begin conceptual layouts and design scenarios using a very detailed model to quickly view the limitations and options that they may need in planning out the future development of the city. From an architectural or engineering perspective, accurate measurements and details can be obtained for future designs or as-builts. Conversely, environmental impacts such as impervious coverages or solar impacts can easily be determined from this reality model. In another example, from a more down-to-earth perspective, or maybe in this case we should say under-the-earth perspective, sewers or tunnels and other very complex structures can now be modeled for design and inspection purposes. In the transportation industry, here a highway design has been modeled. In a civil environment, reality models can be used as-builts or to represent existing conditions and basically throughout the life cycle of the project. Even in the construction phase, reality models can provide quick volumetrics along with other design verifications. Reality models can also be used in manufacturing. Here, the jet engine has been modeled with over 100 images. Conversely, here are 4 examples of entire cities where reality models were created using thousands of images. These models take days to complete on multiple machines. Next, we'll look at how ContextCapture works. ContextCapture generates full 3D reality models from digital images. These images can be taken with virtually any digital camera. There's no special camera needed, no special lenses, virtually any digital camera. Next, we want to look at how we capture the digital images. Acquiring imagery can use 3 main classifications. The first being mobile, the second being ground, and third being aerial. Ground capture is typically used when capturing smaller subject matter, where we can easily move around and capture the subject from all or various angles. This is typically done using a DSLR or perhaps a phone camera or even a GoPro. Aerial capture is typically used where a site needs to be accessed from various angles from above. This is typically done on a site level with a UAV. In any case, the aerial imagery is acquired using cameras mounted on the drone. For larger areas, fixed-wing aircraft can be used for aerial capture and vehicle systems for ground capture. For reality modeling, acquiring the images is not very difficult. In fact, it's pretty straightforward. However, taking these pictures isn't the same or quite the same as taking pictures to be posted on some social media. Here we show ground capture. Ground capture is done with any handheld digital camera, either by walking or driving along the subject matter. In each case, the camera must use a fixed focal length, and images taken must overlap by a minimum of 70%. Here, each rectangle represents where the user stood or positioned himself and the angle of the camera when the image was captured. By combining these images in the software, we generate the model we see. Next, we'll look at using a drone in acquisition or aerial acquisition. The same principles apply to working with a UAV in capturing our images, and that is we still use a fixed focal length. We still require overlap of 70%, and from the air we can use a combination of nadir images and oblique imagery, or solely use oblique imagery. Here we see the UAV flying a mission plan across the site. Down in the lower right, we can kind of, if we look closely, see the poses of the cameras in the air. In this case, some 1,800 images were captured. And as you can see, as the images move across your screen, the images are acquired every so many feet to capture the proper overlap. When the mission's completed, the UAV returns, lands, and the images are extracted from the camera. Want to also take note to, if you are working with a UAV, to follow all FAA guidelines and requirements. Next, we want to give a product overview of ContextCapture. We'd like to show how ContextCapture works, how we go from images to a reality model. So let's take a look. Whether working from sites to cities, ContextCapture processes the digital imagery into a 3D reality mesh. This mesh can easily align with real-world coordinate values and positioning, and in many cases can give very, very accurate, in fact, survey-accurate models. Looking at the workflow, we would be looking at capturing the images, importing them into our master program, where the images are aligned through a process called aerotriangulation. Aerotriangulation is run through what we call an engine, and the second process is what is called the reconstruction process, and this is where we generate the mesh and then texture the 3D mesh to become a textured 3D model. The model can be edited if need be and sent back through and reprocessed for any touch-ups that are needed. Downstream, the workflow would involve using that 3D reality mesh within Microstation environment. We can also generate what's known as an OBJ or collada, and these are common file sharing formats for a 3D model. We can also generate point clouds. Bentley's native point cloud is a POD file, and we also generate other formats as well. So let's take a look at the process in a brief demonstration. To create a reality model, we first create a project. Next, the photos are added to the project. We can add multiple photos in what are known as photo groups. This allows us to add photos of different focal lengths or from different cameras. The software automatically reads the camera specifications such as focal length and sensor size. Once these images are set up in the project, we start the engine. The engine kind of runs in the background, and it allows us to submit error triangulation. Error triangulation is a process where we match or find key points in the images and align those key points. Depending on the number of images, the length or duration of this process will vary. It will also depend on the computer in use. Once completed, we get a list or some statistics on the imagery and the process. We can then view in a 3D format the poses of the imagery, all based on mathematical calculations taken from the images themselves. The last step is a reconstruction. In a basic project, the reconstruction is resized. Obviously, the further from the principal points of the image, the more distortion there would be. So we resize spatially our project, and then we take a look at our memory usage, and depending on our machine, we tile the project, and this decreases our memory use and outputs multiple tiles. We then submit the production, where we can create 3D models, point clouds, and various other formats. Any number of productions can be rerun, so if we choose to rerun ortho photos at a later date, we can easily do this. Again, the duration of reconstruction will depend on the machine or the number of machines being used, and also the number of gigapixels within the project. Once completed, our 3D model can be viewed within the software or a viewer, or it can be viewed in a web browser. The mesh generated from the software is what we call a multi-resolution mesh. So as we zoom in, the mesh gets denser. And this is what allows us to generate entire cities with the software. Before we end the session, it is critical to reiterate and expand on the uses of a reality model, specifically the context model within Bentley software and how it provides a superior workflow. As mentioned, reality models are useful in most every AEC industry. And just as important, is that their use spans the life cycle of the project. From existing conditions to design, the reality model can be used in risk management, helping to identify needs, set performance standards, and provide insight into funding and procurement of funds. Within construction, we can use the reality model to detect changes and to archive valuable construction information at various stages in the construction process. Even at the end of the project, after all work's been completed, reality models provide opportunity for asset performance, 3D inspection, and even training simulation. Bentley Systems has long been known for its federated approach to workflows. With this approach, any number of reality model outputs are easily managed within Bentley's connected environment. Microstation Connect easily manages the reality model in a variety of formats. These would include 3MX, point clouds, orthophotos, and more. Let's take a quick look at a georeference reality model being attached into a Microstation design environment. We'll be using the 3MX format and also the POD point cloud format. Opening of a ContextCapture reality model can be done in the Acute 3D viewer. By doing this, the user gets a good feel of the model and can interrogate it or analyze it in various ways. So within this dialog, distances can be determined and so forth. In this case, because we've outputted the 3D model into a UTM coordinate system, we're working in meters. So basic volume calculations can be done. To make this model more useful, it would be to our advantage to bring it into a design environment. As we said, the 3MX model can be used throughout the life cycle of the project, beginning with existing conditions, moving into design, and then maintenance and so forth. And when we talk about this, we're talking about the model being captured maybe through the same method, maybe different methods, but the same area captured at different stages. So in this case, we have a roadway intersection reconstruction that has been underway, and we've done an initial capture of the intersection. And for our purposes of surveying, this model will accurately do what we need it to. So we can see the mesh within the model is a multi-resolution, and as we zoom in to the mesh, we can see a great amount of detail at the curb line and at the gutters and so forth. And this is our infrastructure. This is what we want to work with, and in this case our model has been georeferenced with control points. So the same model can now be taken into a design environment for review and also design purposes. To do this, we'll open a Microstation design file. From our design file, we can see that we have a geographic coordinate system set. In this case, we're working with North American datum 1983 PA South. This is a survey foot grid, and as such, we have our survey located spatially located within this grid. Now in our case, we use the same controls for our 3MX model, our reality model, as we did as the surveyors did. The survey was completed with a total station, and as you can see by clicking on it, we're georeferenced, and we actually go into Google Earth view, and we can see the area that we're working with. Back to the Microstation file, we want to now attach our survey or our reality model to our survey model and check the survey model for accuracy. We can see that we have our points showing up along with our gutter lines, curb lines, contour lines, etc. So to do this, we attach through the attach dialog and we'll reference our 3MX file. When we reference our 3MX file, we're going to use a Geographic Aec Transformation. By doing this, it'll transform our UTM coordinate grid to our state plane coordinate grid, and we'll see our model attached. And if I select it, we can see our mesh. From the mesh, we can begin looking around and analyzing the accuracy of our survey points. And actually what we would find is that our mesh is quite a bit more accurate than our survey points completed with a standard total station. The reason for this, or the primary reason for this, is the algorithm used within the survey doesn't allow for the correct bending of the lines. We can also zoom and look around and find that the surveyor missed various shrubbery and even a sign in a couple locations. We can use the Microstation analyze commands, and we can also snap or measure any of these errors within our Microstation environment. With the Microstation clip volume utility, we can run a clip volume on our reality model and display a cross-sectional view of our roadway. So to do this, we simply grab our clip volume tool, so in our site, we can now rotate it and we can see our clip volume. We can move across the site. Let's try it again. Go to our top view, clear our clip volume. This time we'll set up a clip volume as a line. Generate the line across our site as a cross-section view. So we'll turn off the back. And now we can look at the section going across our view. And again, we can look at this by rotating it, getting a good cross-sectional view of our roadway. If need be, we can even use our design tools. And let's change some weights. We can move our tools to the plane of the road, and we can capture the existing conditions as they actually are. Okay. So this is how we work with the 3MX model inside of Microstation. There are other ways to add break lines, create surfaces with civil tools, or even bring it into building environment or building tool sets and work with it in those ways as well. So now let's take a look at how we would work with point clouds. So we'll detach our model, we'll clear our clip volume, and now we'll go to our point cloud display, and we would simply load in our LAS or POD files. In this case, I actually have them loaded, so I'm going to just select them and display them. And we can see that with the RGB value displayed, the POD file displays much like the 3MX file. And again, we can begin using our third-party apps or our tools such as Bentley Descartes to analyze the point cloud and work with the point cloud. This point cloud will be as dense as any other point cloud, or can be as dense as any other survey accurate point cloud, and in some cases maybe even more dense. The reality model adds value because it can be used in a design environment, and it's accessible to designers at all phases within the project lifecycle. So now we see how easy it is to work within the Microstation Connect environment with our reality model. It's up to you now to have some fun.